All right. Okay. Good. All right, let's get this started. Okay. All right, good. Everyone can see. Okay, good. All right. So today's class is going to be, we're going to finish up the module today by talking about line integrals and surface integrals. So that's going to be the main topic for today. There's a lot of math and steps involved in line and surface integrals, but I think if we have a very step-by-step process of doing this, I think that it will be fine for everyone. So just keep in mind that what we're doing today, it's one of those things where you're going to have homework problems. Those homework problems can be kind of long, but if you follow the step-by-step process, it's very methodical. It generally works for every type of problem you're going to work on. And so keep in mind that strategy is very important. So if you have a sheet of notes with you today, a sheet of paper out, go through these steps with me as I'm doing them in class, as opposed to just watching them. If you go through them with me, then you'll remember it better. So let's get right to it. Let's talk about what line and surface integrals are. Then I'll take a quick break to just address some of the homework and exam questions. All right. Just give you a little bit of a preview of what we're doing today. So we ended up last time, we finished talking about the different coordinate systems. Okay, we spent a long time on this so that you can understand how the different coordinate systems work. And one nice little summary of what we did the other day is given in this table here. All right, first of all, if you want to convert a coordinate system from one to the other, you can just follow these formulas. There's three different coordinate systems, so 6 possible transformations, and all this stuff is right here. If you want to convert the variables, the coordinate variables from one system to another, that's this column. If you want to convert unit vectors from one to another, that's this column. If you want to convert a vector from one coordinate system to another, you go to this column. And this is the table that you're going to use if you want to calculate gradient, divergence, and curl in the different coordinate systems. We have mainly talked about the formulas for divergence, curl, and gradient, and the Laplacian in the Cartesian coordinate system. But there are also formulas for the same operators in the cylindrical and spherical coordinate systems, but they are different because the length operators in those coordinate systems are different. Okay. I want to go back to this and also indicate to you that this table is super useful. We're going to be using it today for doing surface and line integrals. And the thing that we're going to be focusing on today is the differential length and the differential surface areas and the differential volumes, actually, in all of these coordinate systems. Okay, we talked about this in class last time. It's summarized in this portion of the table here. But these tables will be your friend. These tables will be provided to you on an exam, so you don't have to worry about writing them down. But you do have to know how to use them. Okay, so what's in these tables? Coordinate variables, the magnitude of a particular vector, the base vector properties. They're always the cross products. It gives you the values of those, and it gives you the values of the dot products. How do you calculate a dot product? It's identical, whichever coordinate system you happen to be in. cross product, the formulas are actually identical regardless of what coordinate system you're in. But the differential length, the differential surface areas, and the differential volumes are different depending on the coordinate system. So keep that in mind when you do your homework problems. All right. So in the interest of time, I'm actually not going to spend time on this today, but I did want to show you how to calculate a vector field in spherical coordinates. And rather than, I'm not going to bother opening up the notebook. What I want to do is I want to show you some of the major points of how we did it, because we spent a lot of time 2 class periods ago on how to do plotting in Python. So the focus of this is I want to show you how to convert or how to plot something in the spherical coordinate system or in the cylindrical coordinate system. Now, MATLAB happens to have some conversion functions to go between these 3 different coordinate systems, but Python, you have to roll it yourself. So I just want to show you the quick code on how to do that. First of all, why do we need to do a coordinate transform? Well, whenever you plot something, whether in MATLAB or Python, 3-dimensional plotting, they don't have the spherical and cylindrical systems built in. You have to plot everything in a Cartesian coordinate system. So if you want to plot a function that's defined in spherical or cylindrical coordinates, you have to first convert those vectors, convert those coordinates into the Cartesian system, and then plot it in the Cartesian system. So I'm going to show you the main points on how to do that. And I would like you all to, to do this as part of your homework exercise or just on your own so you know how to use it. Okay. And if some of this stuff is hard to remember, we went over it the other day, so I'm not going to, go over everything in detail. Just quickly mention what the different steps are. So what we have here is we have a vector field in spherical coordinates. Okay. I showed you the other day how to calculate and plot a vector field in Cartesian coordinates, but this is in spherical coordinates. So what we first have to do is convert this vector into Cartesian, okay? We're going to start off by doing the same thing that we did earlier. We create a mesh grid, okay? To create a mesh grid is a series of points in 3-dimensional space. So we are, you can see how many arrows we've drawn here. So the number of arrows corresponds to the number of points in the mesh grid. So the first thing we do is we create a mesh grid. The first statement here, we are saying that we are going to go from, we're going to plot for different values of radius. We're going to plot for different values of theta, and we're going to plot for different values of phi. These are the 3 coordinates in the spherical coordinate system. So we are going to plot 3 values of r between r equals 0.3 and r equals 1. We're going to have 12 values, 12 different values between 0 and pi. Remember, in the spherical coordinate system, the theta variable goes from 0 to pi. It only goes around half a circle. It doesn't go around the entire circle. The third variable, the phi variable, goes around the entire circle. The way that I've done it here is I've gone from negative pi to pi, but you could also do from 0 to 2 pi and it would work fine. And we've picked 12 points going around the circle in the azimuth direction. This is the part where you create the mesh grid. You convert these 3 vectors into 3 3-dimensional matrices that describe the r, theta, and phi values for every single point in that mesh grid. The next part here is you define this electric field in spherical coordinates. So all we're doing here is we're taking this equation and we're writing that equation down. So in this example, we're going to assume that Q is the charge of a proton, 1.6 times 10 to the negative 19. We're going to assume that we're in air, so epsilon 0 is 8.85 times 10 to the negative 12. And here we just define our function. All right, we just put in the formula for the function. Q over 4 pi epsilon 0 r squared. The star means squared. And notice that this formula, the electric field is only in the r hat direction. There's no electric field in the phi hat direction or the theta hat direction. So these 2 are equal to 0. Now what we have to do is just convert those vectors into Cartesian. We also have to convert the coordinates. So these formulas that you see here, x, y, and z, are functions of r, theta, and phi. So you have this formula for x in terms of r, theta, and phi. You have a formula for y, for r, theta, and phi, and you have a formula for z. So we are converting the coordinates into the Cartesian coordinate system. The next part we're doing here is we are converting the vector field into the Cartesian system. And where are all these formulas coming from? Well, you could derive them, or like I said before, you can use your handy, you could use a handy chart. So all we're really doing here is using this. We're using this chart here. This one here. We want to convert from the spherical coordinate system into the Cartesian coordinate system. So we're just using this set of formulas here to convert the vectors over, and this set of formulas here to convert the coordinates over. All right. So calculating those by hand would be really awful, but calculating in here takes just a fraction of a second. So E underscore x, this is just a convention, the electric field in the x direction, the electric field in the y direction, the electric field in the z direction. All right, so we are converting them from the electric fields defined in the spherical coordinate system. And then the last part here is just plotting the vector field. You create a figure, you add a three-dimensional subplot, and then we use the quiver function to plot the vectors in Cartesian coordinates, and then we show the plot. And you can see that the vectors go out like this. All right. Any questions? All right. Great. So one thing I did here is I made all the vectors equal to the same length. I put a parameter here that says length equals 0.2. So you can kind of see that the vectors are similar lengths. If I didn't do that, what would happen is that the vectors on the inside would be massive, and then the vectors on the outside would be really small. You know, because this is a function as 1 over r squared. You know, the ones where r is close to 0 are going to be really, really big. So that's why instead I just plotted them all on the same magnitude. All right, so that is plotting vector fields. I have, you know, I think what I'll do is, in the interest of time today, I really want to get to surface integrals. I'm gonna share the solution with you here real quick. This was an example of how do we calculate the curl of a vector field in cylindrical coordinates. And this is just to show you that you can just use the formulas from this chart. Go back to this chart here. This is from Wikipedia. This tells you how to calculate the curl in cylindrical coordinates. You have to take 1 over rho. Now, rho in this chart is the same thing as r. Okay, they define it a little bit differently in Wikipedia. They use rho instead of r. So you just do 1 over r, daz, d phi. You follow these formulas here, and that's what we're doing here. All right. So this is the formula that's given in given from the chart. Notice there's only a z hat component. The reason why there's only a z hat component is because it turns out these two components go to 0 when you plug in the numbers here. These two portions of the vectors go to 0. You're left with just this third one down here. It's d of r times a phi over dr minus the derivative of 1 over ar over d phi, and that's in the z hat direction. So just follow that formula, and you'll see that that the curl, interestingly, comes out to 0. All right. This is the thing I mentioned to you the other day. It may seem a little bit non-intuitive, and I specifically gave this example because I wanted to remind you of this very non-intuitive thing. We talked about curl. We said if you have something that's spinning around, you know, then it would seem to you that the curl would be non-zero, right? But this was a kind of a special case here where we found that because of this 1 over r function, it turns out that if you were to put a log on here, the way that you test for curl, by the way, is you imagine that these are like flow vectors. And if you were to put a log somewhere, the question you have to ask yourself is whether that log would spin. And it turns out if you put a log here where my mouse is, the log would not spin on its own axis. It would actually, it wouldn't spin. It would just go around the middle here, but the log itself wouldn't rotate. All right. So in other words, like imagine a planet going around the sun. All right. You're not interested in the fact that is the planet going around in a circle. That's not what curl is. The curl is whether the planet is actually rotating on its own axis. Okay. So it turns out that if you were to put a log here, the log would not spin around its own axis. It would just revolve around the center point. And that's why the curl ends up being 0 in this case. Right. The only place actually where the log would actually spin is if you were to put it at r equals 0. But this vector field is defined in this formula. The r is at the bottom, so this vector field is not defined at r equals 0. Right, it's undefined at r equals 0. So that's why you can't calculate the curl at r equals 0, because the field is undefined there. All right, now let's get into a review of integrals. So in electromagnetics, integrals are used to calculate quantities like total charge, electric fields, electrical and magnetic fields. So we have to review how to take integrals of scalar fields as well as vector fields. So let me have a show of hands. How many of you did integrals of scalar fields in your calc class? Okay. Okay. Let me ask it another way. How many of you did? How many of you did one-dimensional integration? How many of you have done one-dimensional integration? Okay. All of you. Good. So I want to make sure we're there. How many of you have done two-dimensional integration? All right. And 3? Okay. Same number. Okay. Yeah. So the 2- and 3-dimensional integrals are what we're going to go over today. That's what you do in multivariable calculus. And when you do those integrals, the way you learned it in calculus, that's for scalar fields. It's for scalar quantities. Now, for the purpose of this class, I have a feeling that many of you haven't done vector fields before. We have to talk about how to do integrals of vector fields. And so we're going to do these things called line integrals of a 2D or 3D vector field, and then we're going to be doing surface integrals of a 2D or 3D vector field. Actually, we're going to be doing the surface integrals first and then the line integrals. Okay, so this first part will be a review, I hope. If not, just go through it, review the videos, and hopefully that will become clear to you. And then these will be probably new to you. Now, the key thing to these, I remember the first time I took a calc class, and it seemed like these double, triple integrals, and then when we get to these vector integration, it's a lot to remember. Sometimes like this is the thing that gives students the most trouble in this class, because there's a lot of calculus in this class. And so for that reason, I think it's very important that we actually go over these concepts, and you have this step-by-step procedure on how to do these things, okay? And, I think it's been a couple of years since I taught this class, and I have to remind myself on how to do some of those problems, because they are involved. There's a lot of steps to them, okay? So I want you to understand this step-by-step process and how to do them, so that you practice on that step-by-step process a few times, and then it appears easy to you. All right. So let's talk about scalar fields first. Okay, we're going to be doing this portion first. How do we do integrals on scalar fields? And if this is review to you, great. So when we do integrals of scalar fields, just want to remind everyone that this is what a one-dimensional integral looks like. Integral of f of x dx. Okay, and what that intuitively means is that you are taking the area under the curve. So if you have a curve that looks like f of x like this, and imagine that we're just drawing an arbitrary curve, the actual formula doesn't matter, but just know that the f of x can be above, it can be above y equals 0, so it can be on the positive side of y equals 0, or the x-axis rather, or it can be on the negative side of it. So if it's on the positive side, the area under the curve is going to be positive. If it happens to be negative, if the value of f of x is negative, then it's going to be on the bottom side of the curve, and that integral is the integral for this portion is going to be negative. This is a negative area under the curve. This is a positive area under the curve. So if the positive and negative areas under the curve happen to be equal to each other over your range of integration, then the integral can actually end up being 0. All right, so when we talk about taking the integral, we talk about taking the integral from a point A to point B, right? So we'll say A to B. And so that what we're essentially doing is summing up the areas under the curve between A and B. So intuitively, what that would mean is we're going to add up this blue area, add up this blue area, and subtract out this orange area. And that will be the integral. All right, that's on a scalar field. So eventually we're going to talk about the vector field as well. What if we take this into 2 dimensions? If we talk about 2-dimensional integrals, we are no longer talking about the area under the curve. We are talking about the volume under the surface. Okay? So imagine, like, if you have a function f of x, y, so we are going to take, just to be clear here, sometimes in math, they just approximate that or just shorthand it with a single integral sign, but you can also have 2 integral signs there, and that makes more sense to me. A double integral with respect to x, with respect to y of this function, f of x, y. So let's remind ourselves that an f of x, y is a surface. Okay, f of x is just a line that's plotted on the xy axis. F of xy is a 2-dimensional surface that's plotted on the xyz axis. All right, so imagine that this little, it looks like a little saddle here, but that is your 2-dimensional surface. When we take the 2-dimensional integral over a range of x and over a range of y, so let's say we're going to take the integral with respect to x from x equals a to x equals b. So let's say this is our x-axis, and this is our y-axis. So we're going to take the integral from x equals a to x equals b. And then we're going to take the integral from y equals c to y equals d. So this would be y, this would be equal to d, and this y value would be equal to, I'm sorry, this is equal to d. This y value is equal to c. All right? So we are taking the integral with respect to 2 variables. And the physical meaning of that is that that ends up being the volume under the 2-dimensional surface. So the volume under the saddle here. Okay, any questions on 2-dimensional integrals? What it intuitively means? We'll do some examples of them. All right. Now the 3D integral. The 3D integral, it's not really possible to just draw it because the this one was an area. Like the integral of a 1-dimensional function was an area. The integral of a 2-dimensional function was a volume, and it turns out that the integral of a 3-dimensional function is something in 4 dimensions. Okay, so we can't see things in 4 dimensions. So what you can think about when you think about a 3-dimensional integral is you can think about summing up if you think about the integral of a 3-dimensional function, you are adding up all the things in a 3D volume. Let me give you an example. Let's say you had an arbitrary 3D volume, okay? And you want to find out what the weight of that object is. You want to find out what the weight of that object is. Okay, the weight. One way of finding the weight is that you can take the 3-dimensional integral of the density. Okay, the density, what's the units for density? Yeah, kilogram per centimeter cubed. That's exactly right. So that tells you that the density is the weight per given volume. So if you take the integral of the density, the triple integral of that with respect to 3 dimensions, and you're integrating over your 3-dimensional shape or 3-dimensional volume, then that will give you the total weight. Okay, so that's one example of where 3-dimensional integrals are used. You're summing up all the certain properties of a 3-dimensional volume, and that gives you another quantity. All right, but there's no easy way to really draw that, like we can draw 1D and 2D integrals. The way that we do 3-dimensional integrals is we show this a triple integral sign, f of x, y, z, and then we have dx, dy, dz to show that you are integrating over 3 variables. Okay, questions? All right, let's do an example of a triple integral in Cartesian coordinates. So this is the part where I just like for everyone to just remind themselves how to do this just go ahead and try this on your own. We'll go through the steps. So I just want to make sure that everyone is attempting these on their own. So suppose you have a function f of x, y, z, and that's equal to k times z. So this is a three-dimensional scalar function that we just talked about. K is a constant, any constant. Evaluate the triple integral of this function in just a three-dimensional volume. All right. Now the strategy for doing this is you have to ask yourself, what is the function you're going to integrate, and what is the range that you're going to integrate on each of the three variables? You know, triple integrals means you have to actually do three integrals, one on each of the three variables in the coordinate system. So in this case, we have, we have a Cartesian coordinate system. This is your x-axis, y-axis, and z-axis. And this is asking you to find the triple integral of f in the volume shown. So in the volume shown, we can just write this down. Give it a second. Okay, so what is the function you're going to integrate? Well, we have that function already, so this is a trivial step here. What is the range of integration? We want to go from, you can write this down as like, we're going to integrate from x going from 0 to 4. Our y is going to go from 0 to 4. This is a simple problem. And z is going to go from 0 to 4. All right. And the next step after that is to actually do the integration. So let's talk about how to do the integration here. I'm just going to show you the different steps. Okay. All right. Thank you for that. All right. Let's just show this here. All right. So you guys can jot some of this down, but I want to go through it step by step. And like I said before, I intentionally don't put this in the slides because I want to make sure that everyone's watching the lectures and going through it step by step. So how do you do a triple integral like this? So the first thing you do is you lay out the three integral signs, and then on the right side you have your dx, dy, dz. All right, so let's start with that. We are integrating from, you put down dx, dy, dz on this side, three integrals on this side, and then you put your function in the middle. So this is your function. All right, and when you do this, the main thing to remember is what is the order of integration that you're going to do. When you do triple integrals, you go from the inside out. All right, and you have to choose your variables appropriately so that you can get the integration properly. Now, in this particular example, it actually doesn't matter the way you do the integration, what order you do the integration. So you can choose any arbitrary order. So let's just do this simple example. We just start out with dx, dy, dz here, and the thing to note is that this, when you say dx, you're going to start off with the inner integral here. You're going to differentiate that with respect to x. So think about it like you have the dx over on this side, on the right side, and on the left side, the first integral that you have is going to be x equals 0 to 4. In fact, a lot of times people will specifically say x equals 0 to 4 rather than just putting 0 and 4 here, just so that it's perfectly clear that this particular integration is for the variable x and not for one of the other variables. All right, so you're going to integrate from x equals 0 to x equals 4 of k times z of dx. And what we're going to do for the time being is we're just going to ignore everything outside here. We're going to ignore dy, dz. We're going to ignore these integrals here. We're just going to do what's in the brackets. All right. So I'm just going to make sure that everyone has this written down. Okay, the next step is you're going to actually do this integral. So what are the key things here? I'm going to write this out here. K z dx. So we are integrating with respect to x, okay? So when we integrate with respect to x, we treat everything else like they're constants. K is, of course, a constant, but z is also a constant because we are integrating with respect to x. So we have to treat this as if it was just a these are both just constants. So what's the integral of a constant? It's just x. That's right. So this is going to become k z x, and x is going to go from 0 to 4. All right, and that's what we have here. That's what's shown here. All right, and how do you evaluate this? Just to remind you, this is going to be kz x from 0 to 4. You substitute in 4, and then you substitute in 0, and you subtract the second one. So 4 minus 0. So this is your function. You're going to substitute in 4 for that function here, and then you're going to substitute 0 for x here, and then you subtract out the lower substitution. Okay. Everyone with me so far? All right, good. This should all be just a simple review here. All right. Now, once we have this, the result of this is 4kz, and that's what we have here. All right. Now we're done with the first integral. All right. So we've knocked out one of them. Now we have to do the other two. So when we do this integral, we just think about this portion here. Ignore the dz there, and we'll take care of that later. So 4kz dy. What's the integral of that? Well, it's just 4kz times y, because 4kz, these are all constants. You know, when we're integrating with respect to y, there's no y in this function. So this is just a constant. We treat them as constants. So this becomes 4kzy. We evaluate that between y equals 4 and y equals 0. And we end up getting 16kz here. And then we do the third integration like this. The third integration is with respect to z. All right, now here's the difference. Notice the difference here. This last one, when we do this, our function is 16kz. We are integrating with respect to z, right? So what's the integral of 16kz with respect to z? 8kz squared, right? This function z becomes the z squared, right? So we just have to keep that in mind. All right. So sometimes when you do these triple integrals, sometimes you're going to get situations where you just have constants in there, but sometimes you're going to have functions that are where you actually have to do the integration. We don't have any integral tables in the notes, but like if there are some complex functions that you need to know the integral of, you can look them up in integral tables. And if we'll have integral tables on the exam if you need them. So the integral of 16kz, 16 and k, we treat them as constants, becomes 8kz squared. And that's evaluated from z equals 4 to from z equals 0 to z equals 4. So I'll just show you the intermediate step here. 8k 4 squared minus 0 squared. All right, and that's how you get your 128k. All right, so just to remind ourselves, you do the integration from inside out. And this is a 3-dimensional example, but you could imagine just doing, if I asked you to do a 2-dimensional example, you should be able to do that as well. All right. So the next example I'm going to show you is a triple integral in cylindrical coordinates. We did one in the Cartesian coordinate system, and we're going to do another example in the cylindrical coordinate system. All right. And in this example, I want to show you in one useful way, one utility of double and triple integrals. You can use double and triple integrals to calculate the area of a surface. You can use triple integrals to calculate the volume of the volume of a three-dimensional shape. So the question here is, can we use a triple integral to derive the formula for the volume of a cylinder? And this is the simple example where we are going to use a triple integral to find the volume of this shape here. All right. Now we already know that the integral of a cylinder is pi r squared times h, right? So we know that from geometry. But this is just to show you that you can use triple integrals to do the same thing. In fact, triple integrals are used to derive the volumes. Moreover, is that if I gave you some portion of this cylinder, you can use triple integrals to do that. So let's say instead of saying what's the volume of the entire cylinder, what if I told you that I only want you to calculate the volume of this this portion of the cylinder? Not the entire cylinder, but just this Pac-Man, three-dimensional Pac-Man structure that I cut out. Then you can't use your geometry formulas anymore. You have to use three-dimensional integration. All right? So, but let me just redraw this again. So we are just looking for the volume of the cylinder, and we're going to use three-dimensional integration to do that. So here's your x, y, and z here. All right, so this is something you may or may not remember from calculus, but if you want to calculate the volume of an object, what you have to do is you have to take the integral of the function 1. So to find volume, you integrate the function, the unity function, 1, and you integrate that over 3 dimensions. So our strategy, I have this in the green box here. It's copied over from the previous slide. The strategy is the same. You're going to integrate a function, or you have to decide what function are you going to integrate. So in this case, to find the volume, we integrate the unity function, just 1. The second step is what is the range of integration you're going to do on the 3 variables. And then step 3, if we want to be explicit about it, integrate inside out. Integrate inside out. All right, so the function that we're going to integrate is just this function 1. And then when we figure out what range of integration we're going to do for the 3 variables. All right, so this is the key thing here. We want to find the volume of this entire cylinder like this. So this distance here is A, radius is A. So in order to cover this entire volume, we want the range of radius for that cylinder is going to go from 0 to A. Does everyone agree with that? Right? Yeah. We're going to go from R equals 0, which is the center, to R equals A, which is the side of the cylinder. So that's our range for R. Okay. What is going to be our range for phi? So if we want to get the entire cylinder, what is going to be our range for phi? 0 to 2 pi, right? Because we want to go, phi is a variable that goes in this direction, right? We want to get the volume of the cylinder, we want to go around the entire circle. So we have to go from phi is equal to 0 to 2 pi, all the way around the circle. Now, remember I gave you that example of the Pac-Man shape? You know, if I had, what if you want to find the volume of just this portion of the sphere, for example, this portion of the cylinder, for example, going down like this, not the entire cylinder, but just a portion of it, then you would integrate from those values of phi, not all the way around the circle, just a portion of the circle. All right, we'll have another problem like that next, so don't worry about it. So right now we are integrating across the full range from 0 to 2 pi. And how about z? What is going to be our range for z? It will go from 0 to the height of the cylinder. All right. So now that we've set up our ranges of variables, we can set up the equation here. So notice the first thing I did here is I have z equals 0 to h, I have r going from 0 to a, and I have theta going from 0 to 2 pi. Let me just fix this here. This should be phi. Just so, you know, the theta is used in the spherical coordinate system, so let's just say this is phi. Phi is what's used in the cylindrical system. Okay, so our phi is going from 0 to 2 pi, r is going from 0 to a, z is going from 0 to h. Now this dv, how do we deal with that dv? Look on chart. All right, so let's go back on our chart here. I mean, many of you will probably have this memorized, but I'm just trying to give you all the step-by-step procedure. So we're in cylindrical coordinates here, all right? Cylindrical coordinates, what is our differential volume, dv? Look it up on the chart. It's r times dr times d phi times dz. So that's what we have here, r times dr times d phi times dz. That is the differential volume element in cylindrical coordinates. We went over the details of that last class, so I'm just looking it up on the chart today. Notice the difference between the Cartesian system. The Cartesian coordinate system, the dv, the differential volume element was just dx, dy, dz. Don't mix that up in the cylindrical or the spherical coordinate system. It's not just dr, d phi, dz, and they're different. You have to look them up. Yes, question?
For the integral order, shouldn't r equals 0 to a be the first integral?
Absolutely, absolutely. And I'm doing this example here to show you the first step that you do. You take dv and you just substitute in r, dr, d phi, dz. So at this point, what you could do, you know, I apologize, this might be a little bit confusing. I say here that you should integrate inside out, and that's what we did in the previous example. But I want to show you another way of doing it too in this particular example, where you can just rearrange them and separate them and do them in parallel. Okay, so if I were to do this using the approach that I showed you on the last slide, then I would integrate from the inside out. So then I would change this. You know, I would go from z equals 0 to h. I have r dz here because our function ends up being r. And then then the next one I would integrate is dr. So with dr, I would write down r equals 0 to a. And then I'd put down my phi. So I say d phi. Phi equals 0 to 2 pi. All right? And then I could go inside out just like we did on the last slide. Okay, but I just want to show you there's different ways of skinning a cat. And in this particular problem, what we're going to do is we're going to take the three integrals that we would normally do inside out, and we're going to just do, we're going to turn them into the product of three different integrals instead. So what we do here is that we take, you know, this is our function here. We take all the ones that are related to the phi variable, and we put that into the integral here. We have an integral with respect to phi. We multiply that with an integral with respect to r. Multiply that with an integral with respect to z. All right, these are equivalent. You can do the inside-out approach, or you can do it the separation of variables approach. Both are mathematically valid. All right, so what we're going to do here is we notice that in this formula, we see that there's a portion of the formula that's just a function of r. This r dr is just a function of r. So we put that into the integral with respect to r. And then we have a portion that's just related to phi, the d phi. We put that in the integral here, and this is just related to z, dz. This approach will not work if you have a function where there's multiple variables that are convolved together. Right, so let's say you have like, r squared plus phi squared, or r squared times phi squared, where the two variables are being multiplied together. Then those two variables are convolved together. You can't do that. So, but in this one, you can separate them out like this into different parts, so it's easy to solve. All right, so now you have three different integrals that are just multiplied together, and you can do each of these integrals in parallel. The integral of dz from 0 to h is just equal to h. The integral of d phi from 0 to 2 pi is just equal to 2 pi here. And then this one here, the integral of r dr, so that r becomes r squared over 2. And you evaluate that from 0 to a, and you get a squared over 2. So this, this should be a, sorry. Pi a squared h. A is the radius of the cylinder. All right, so any questions on how to do that? You all need a second to copy it down, that's fine. Yep, question.
So the order is R, phi, Z, like normally, like based on the sheet. Ah,
good question. What is the order? Yeah, like the table will list R, dr, d phi, dz here like this, but they're multiplied together, so you can rearrange them however you want. So what we did up here is we, in this example, what I showed you is if we were going to use the inside-out approach, then I would have the z variables on the inside, and then the r variables, and then the phi variables. Yeah, you rearrange them. Yes.
We just have to organize the range with the correct variable.
With the correct variable, that's right. Yeah, you notice how I have the z one, the dz is on the inside, and then I integrate with respect to z. After I'm done with that, then I have the dr, then I integrate with respect to r.
Doesn't matter which order, as long as the...
Yeah, it doesn't matter what order. There are certain cases where you have to be careful of order, but not in this one. I'll show you an example of that next, where you have to be careful of the order. Yes?
So this was the case where our function was just one, right?
Yes. Right. When you're trying to find the volume or the area of something, you just integrate the unity function. In this case, over 3 dimensions to find the volume. If I asked you to calculate the area of a surface, you integrate the unity function over 2 dimensions. Unity function is a fancy way of saying 1. All right. Another example here. This is an example in spherical coordinates, and I like before I'm going to, I'll just move these out here so that you all can see the solution. I generally try to, if there's a lot of writing here, then in order to save myself time in class so I can focus on the process, I don't bother, sometimes I just write them out on the slides, easier for you to see. But that being said, I want to focus on the process, the step-by-step process. Okay, so we did an example of a triple integral in Cartesian coordinates. We did an example of cylindrical coordinates. Now we're going to do an example in spherical coordinates. All right, and spherical coordinates is usually the most math involved, most steps, but the process is pretty much the same. So our process is, what is the function to integrate? What is the range? And then set up the integral. And you can set it up inside out or parallel. whichever way you want. Same strategy, okay? Just in a different coordinate system. All right, so this example has to do with like quantum mechanics. You know, quantum mechanics, they talk about electron clouds. You know, that there's a nucleus in the atom and then there's an electron cloud around it. And, you know, if you take my class on electronics, we talk about, you know, a little bit of that, like that there's high probabilities of finding electrons in certain places and not others. So this function describes that. You know, you don't have to know anything about quantum mechanics. All we're doing here is we're integrating a function. All right. So here, what we're doing is we have this function rho, and this function rho describes the charge density. Now, what's the concentration of electrons? And you notice that this function is a function of r, okay, in the spherical coordinate system. This is the radius r. It's also a function of phi. Clarify that this is phi. All right, and there's also a constant a. This is, remember, this is just a constant. Treat that as a constant. All right, so the question is asking, if we have a charge density, if you want to go from charge density to total charge, you have to take a three-dimensional integral. Just like I gave you that example with before, I said, if you have the density of an object and you want to find the weight of it, you have to take the three-dimensional integral. So here we have a charge density, and we take the three-dimensional integral to find the total charge. All right. So the first question is, what is the function we want to integrate? Well, we are given the function to integrate. So these are trivial. The first question is trivial. That'll become more complex when we start getting into line and surface integrals of vector fields. So for right now, the function to integrate is just given to us. The second thing is, what is the range of integration? All right. Now this one we have to look at are three variables in the cylindrical system. So we have the variable r. What are the other two variables in the cylindrical or the spherical system? Sorry, theta and phi. Right. All right. So let's be careful here. So this is saying assume that a cloud of electrons is confined in a region between two spheres of radii 2 and 5 and has a charge density below. So if we were to draw that out, all right. So imagine we have a sphere of radius 2, and then we have another sphere of radius 5. So it's another sphere that's like a little bit larger than the first one. And what we're interested in is we are interested in finding the total charge in this region. Not the entire sphere, but the region between the two spheres. Between radius 2 and radius 5, okay? So what is our range of r? 2 to 5. You got it. 2 to 5. Good. All right. What is our range of theta? 0 to pi. Why is it 0 to pi? We want to go around the half circle. That's right. So 0 to pi means the full range of the sphere. Right? When we talk about the spherical coordinate system, 0 to pi, the theta variable goes from 0 to pi, but the phi variable goes all the way around the circle, 0 to 2 pi. That's how you get a sphere, a full sphere. You can look back to that lecture if that's something that you're confused about. So we are going to go around the full range of theta. How about phi? Are we going to do the full range of phi? Yes, we're going to go around the entire sphere, right? So 0 to 2 pi is going to be our range there. So if I said like, well, we're going to take only the top half of this part in the z is greater than 0, just the top half of it, then your theta variable would change. Your theta would go from 0 to pi over 2 instead of 0 to pi. Right? So just it's important to have the range of integration set. All right. So we're done with the second step. Now we set up the integral, and we can solve it inside out or in parallel. So I'm just going to highlight the main portions of this. The total charge Q is equal to the triple integral of rho dot dv. Triple integral of rho dot dv. But this time we are doing it in a spherical coordinate system. So our dv is something we have to look up on the chart. All right, our differential volume in spherical coordinates is listed here. R squared sine theta dr d theta d phi. There you go. That's what we have here. We're using the differential lengths, the differential volumes from the chart. All right, and we have our function rho here. All right. So the first step we did here, we put in our differential volume. All right, and then we combine them together, and you get r squared sine theta dr d theta d phi. So this is read just from the table here. Okay. Now I also plugged in the rho function. The rho function is a over r to the fourth cosine squared of phi. So I just have that in here. So this is our function, and then this is our dv. All right. So far just substitution. All right. Now, what I also did here, I want you to notice that is that notice the order of the variables here: dr, d theta, d phi. So I'm using the inside-out approach here. So my first integral that I do here, right? I have dr's on the inside, so my corresponding integral also has to be with respect to r. So r is equal to 0.02, r equals 0.05. I'm sorry, I should have put 0.02 here. We're using units of meters here, so sorry for that. 0.02 to 0.05 is the range of r that we're going to do here. All right, so we're going to do inside out. So we're going to work with the R one first. And then we're going to do the theta, and then we'll do the phi after that. So our first step is to integrate everything with respect to R, treating everything else as a constant. Now, the way that we can do a little bit of simplification here is we can take these functions. We have the sine of theta. We have cosine squared of phi. These are not variable. These are not functions of r, right? So it turns out we can take them out, as I mentioned on the previous slide, because they are just acting as constants. And if you were to keep them in here, you'd get the same result. So what we do here is we just take this cosine squared of phi here, and we're going to move it out. And we're going to take the sine squared of phi here, and we're also going to move that out as well. So that what's left in here.
You should also take out the a.
Yeah, we could take out the a as well if we want to, because a is just a constant. I left it in here, but you could also take out the a if you wanted to. Absolutely. So what we have left in here, we just have this function, simple function of r, and we are going to do this integral first. So a of r squared, a over r squared dr, and we just do that integral first. These problems are long, but they're just a series of simple steps. So we first solve this integral here, ignoring everything outside of it. And when we do this integral, the integral of 1 over r squared is negative 1 over r. So we get this here. There should be a negative 1 over r. Yeah, that's going to carry down. This is, I'll fix that there. So we're going to take the integral of this as a over r squared dr. So this is equal to a times negative 1 over r. And that 1 over r is evaluated from 0.05 to 0.02. And now this is out of the integral. Everything else is left inside. So we can figure this out separately. So a times negative 1 over r evaluated from 0.05 to 0.02 is going to be negative 1 over 0.05 plus 1 over 0.02. All right, everybody with me so far? All right, so we're just evaluating this. Now we also look at what's inside the integral here. Our next thing that we need to do inside the integral is we need to integrate with respect to theta. So we're doing the inside-out approach. So we are going to integrate this portion here with respect to theta. Notice what I did here. Notice what I have here. The phi variable is outside of here. So we're going to keep things. We're trying to keep things simple by just integrating the stuff that's with respect to theta, because everything else is we treat it as a constant. All right, the integral of sine of theta. What's the integral of sine of theta? Just want to make sure everyone's awake. Negative cosine of theta, right. So, you know, if we're going to skip over the step here, and that's how we get our negative cosine of theta here. All right. I just showed an extra step here, you know, or not. All right, that's where our negative cosine of theta comes from. All right. And that's evaluated from negative pi to 0. Inside the integral, now we're just left with another simple integral, cosine squared of phi d phi. Now, I shouldn't say this is totally simple, because this cosine squared of phi, that may or may not be something that you remember off the top of your head. Does anyone know it off the top of your head? Okay, so if you did calculus, what's that?
Is it cosine 2x sine 2x?
Something like that. Yeah, you got this. It's what it is. You know, down here, this is actually the solution for it. So something like this. If you don't remember how to take the integral of a particular function, you can look it up on an integral table. That's what I did here. Right? There's a mathematical property that you can use to transform cosine squared of phi into a function of cosine of 2 times phi, and then use that to figure out the integral. Right, but sometimes, like, you know, this is not a math class. It's the point of this is not to do derivations. The point of it is just to find the solution to the problem. So you can look this up on an integral table, and the integral table will tell you that the integral of cosine squared of phi is equal to phi over 2 plus sine of 2 phi over 4, and you evaluate this between 2 pi and 0. All right, so you're going to end up getting a solution here. Now I made this subtraction mistake here. So this is going to end up being a positive, and so all of these numbers will actually be positive.
Where does the C come from?
Oh, the C is just units.
Oh.
Yeah, it's coulombs. Yeah, this is just to remind you that I want to see units when you guys solve problems in class. All right, so if stuff about this is not clear, you didn't have time to write all of it down, then just go over this in the video. Just make sure you know that step-by-step process, okay? Find the function to integrate, figure out the range of integration, and you set up the integral with the differential volume and the differential lengths, and then you you go inside out. All right, so I just want to touch again on this important part. You can just look up, the differential volume. Whenever you have a dV here, of course, you can just look up the differential volume. But you can also express a differential volume as a product of differential lengths. This becomes useful if you're integrating just over 2 variables instead of 3 variables. Let's say I asked you to only integrate over r and phi, and not over theta. All right. So if you want to, whenever you integrate with respect to r, your corresponding differential length is dr. Whenever you integrate with respect to theta, you're going to be using this differential length r d theta. And then whenever you want to integrate with respect to phi, it's going to be r sine theta d phi. So these are the 3 differential lengths. You multiply them together, and you get this differential volume here. Just want to go back. I'll go back to the chart again and make sure that this is clear. All right, this chart gives you the differential, the differential lengths. All right, in the Cartesian coordinate system is just x hat dx, y hat dy, z hat dz. But in the spherical coordinate system, you can say that whenever you're going to integrate over the r variable, you're going to have a corresponding dr. Whenever you integrate over the theta variable, you're going to have you need to have an r d theta, not just a d theta. When you're going to integrate over the phi variable, you need to have r sine theta d phi as your differential operator there. All right, this will become clear in some of the other examples. I'm showing you a lot of examples so that we're all good on this. All right, a third example. We're going to be doing a triple integral in cylindrical coordinates. And this time, we're not just going to find the volume of a cylinder. We're going to do a slightly more complex example, so you can see the value of where integration is useful. Excuse me. Where integration is useful. Okay. Oh, by the way, have we all the homeworks, are they still out there? Okay. Is your name, remind me your name? Carrie. Carrie. Yeah. I thought that's right. Yeah. So Carrie, have a look at if your homework happens to be in that pile over there, if you haven't gotten it already.
Oh, that one.
Yeah. Oh, you were talking about turning in the homework.
I have to turn my homework, yeah.
Okay. Yeah. If any of you have not turned your homeworks in, you can just drop them off at the front here. All right. And like I said, I'm going to post solutions to the homework for homework 0 and homework 1. Thank you very much. So that you have them to study for your exam. Okay. The grades for homework 0 has been posted to Canvas. The grades for the little Python assignment has also been posted. So as we get the grades, you'll be able to see them in the grade book. Before I forget, the exam, and some of you were asking about the exam, it is originally scheduled for next week, but I think we need to have a little bit more time to finish up this module, so I'm postponing it to the following week. Okay? Probably the following Wednesday. Right? If we get it, if you all need some time to review a review sheet, I can work on that and send that out. And also, the main thing is to make sure that you're doing these homeworks. Not just get the answer, make sure you can do them without the help of the solutions, and practice them a few times, and in your head a step-by-step process. This is one of the things that I've found that separates the students who do really well on the exams versus the students who don't do as well on the exams, is that when you do the problems, after you do the problem the first time, take a step back and say, how did I solve this problem? What was the step-by-step procedure that I used in my head to solve this problem? So that way, when you see a problem that you don't know, that you can apply that same step-by-step procedure to figure out the answer. That's why we're talking about strategy here. What is a strategy for problem solving? So I'm giving you an example here, but come up with your own strategies for problem solving that make sense to you. This particular strategy works fairly well on a range of problems. All right. So the third example we're going to do is we're going to calculate the volume of the region of intersection between the red and green volumes. The red volume is a cylinder with radius 1. So you can see here that we have here like this, we have a cylinder with radius 1 that's shown in red. The green volume is a paraboloid defined by the function z equals 4 minus r squared. So a paraboloid is a parabola that has been rotated around the z-axis. And so it's a volume that looks like this in the green here. All right. And you can see that the shape of this parabola z equals 4 minus r squared. It's your typical quadratic function. Right? It's just turned upside down. And so what the question is asking you here is, what is the volume of the intersection between the red volume and the green volume? Right? So this is an example of a problem that where you cannot calculate the volume just using a simple geometric formula. If I asked you to calculate the volume of a cylinder, you don't need integration to do that. I showed you an example of how you can use integration to do that, but you don't need integration to find the volume of a cylinder. And this is an example of something where you have to use integration to find this volume. All right, and I'd probably give you something like this on your exam because, I don't want you to just use simple geometric formulas that you know off the top of your head. So the strategy is the same. What function will you integrate? So let's start with that. What is the function we are going to integrate to find volume? Nope. It's not going to be z equals 4 minus r squared. If we want to find volume, when we wanted to find the volume of the cylinder, what was the function that we integrated? We integrated the unity function 1. So that's going to be the function we're going to integrate. We're going to integrate the function 1. Now we're going to get into the range. This is where the range starts to get kind of interesting. Are those things going to go away? Oh, I need to move them away. Here, I'll make them disappear. I'll do that. Be easier. All right. Okay. There we go. That way I don't have to move them. All right. So the first thing to do is select the limits of integration. Now, this is something where it's a little bit different. All right. Now, so here's how we're going to do it. We are going to integrate from 0 to 1. Our r is going to go from 0 to 1. Actually, let's take that back for a second. Let's do the middle one first. What is the range of phi we're going to integrate? We're going to be going around the entire circle, right? The entire z-axis, and not a portion of it. So that's why we definitely need to go from phi is equal to 0 to 2 pi. Now, the other parts of it become a little bit more, we have to think about them a little bit more. All right, let's going to zoom in on this a little bit. What is our r going to be equal to, and what is our z going to be equal to? If we just use a constant, if we just go from r is equal to 0 to 1, or let's say if we go from z equals 0 to 4, okay? Let's say we do z equals 0 to 4. Then what we'd end up doing is we'd end up with the volume of a cylinder. If we use r equals 0 to 1 and z equals 0 to 4, then we just end up with the cylinder. That's not what we want. We want the volume of the intersection of this paraboloid with the cylinder. So we're going to have like this small cylinder down here, but we're also going to have a paraboloid type geometry up here, all right? So this is where our regions of limits of integration become important. So the way that we're going to do this is we're going to say we're going to integrate from r equals 0 to 1 right? So we're going to integrate from r is equal to 0 to 1, but our z is going to depend on that r. All right, this is the most confusing part about this problem. So this is the key part we have to understand. We want to find the volume under this surface here, like this. Okay, so we have to integrate. We're going to think about integrating from r is equal to 0 to 1. So all the values of r within the cylinder, but the z value is not going to be constant. The z is going to go from 0 to 4 minus r squared. That's the key. You don't want to get this entire thing. You don't want to get this entire cylinder here like this. You only want to get the region below the paraboloid. So that's why we're going from z equals 0. Z equals 0 is down here at the bottom of the cylinder, but the maximum value of z is going to be from 4 minus r squared. That's the key.
That's why we want to integrate it first.
That's why you want to integrate it first. That's correct. Yeah, so that brings me to the next point. When you have problems like this, the difference between this problem and the previous problems is that in the previous problems, your range of integration was all constant. They were all just constants. In this case, your range of integration is actually a function. So z is going from 0 to 4 minus r squared. And when you have situations like this, you actually have to make this one the inner integral. Okay, why? It'll become clear once we solve this. But in short, what the reason why you do this is if you make this the outer integral, what's going to happen is that after you do the outer integral, you're going to be left with this variable r. You don't want that. So you actually want to. You see how this is a function of r squared. You actually want to do this integral before you do the r integral, before you do the integral with respect to r. All right, so that's why I'm suggesting making this the inner integral. All right, so after that, you know, you're going to set it up as same as before. Your volume is going to be the triple integral of 1 times dv. You know, we're integrating the unity function. And that's going to be equal to the differential volume element in cylindrical coordinates as r dr d phi dz. We looked that up on the chart. And now we're going to put in our limits of integration. So this is another key step here. We're going to put in our limits of integration, and we're also going to order the way that we're going to do the integration. So as I said before, what we're going to do is notice how we put the dz in the middle. We put it all the way in the inside so that we can do that integration first. All right, and after we do the dz, then we will integrate with respect to r. If we do it that way, then after we do the r integration, then we'll no longer have a function of r anymore. All right, everybody with me? All right, so we talked about the key steps. Now we talked about the other key step, which is making sure that you put whatever your range of integration that has a variable in it, then you put that on the inside. All right, the rest is just math, so I'm not going to spend too much time on it. The integral of dz, well, actually, maybe this one a little bit. So dz, the integral of dz is just z. And notice we integrate that we evaluate that from 4 minus r squared, from 0 to 4 minus r squared. All right. So what does that leave us after doing this after doing this substitution here? This now leaves us with 4 minus r squared in here. So we have a function of r, right? When we have this function of r, and then we integrate with respect to r. So our next integration is going to be with respect to r. Now, once we integrate that, now we're no longer going to have an r in there, right? That's the reason we put the z integral on the inside. All right, so the integral of 4 minus r squared, you evaluate this first. It's this is equal to 4r minus r cubed. So this is where you get the 4r minus r cubed. And I'm highlighting all the main differences between there. And the other thing we did here is we said, oh, this d5 variable, that d5 variable is unrelated to this one. So we can actually take that out and do that in parallel. So that's where the we have two integrals that we're doing in parallel with one another like this. So the integral of d5 from 0 to 2 pi, this is just equal to 2 pi. And then the integral of this function, you can solve that fairly easily. It comes out to 7 over 4. And so you end up getting 7 pi over 2 as the volume of that sphere. Okay. Any questions? Yes.
Is there an instance where you don't start with the unity function?
Is there what?
Is there like a problem that you don't start with the unity function first?
Is there a problem that we don't start with the unity function first? Yes, definitely. This last example, I said like where I'm actually giving you the function to integrate. So I'm saying integrate this function in 3 dimensions. So I'm giving you that function, and this particular function describes charge density, and I'm asking you to figure out the total charge. So you have to integrate that in 3 dimensions. But if I'm asking you to figure out volume, or I'm asking you to figure out area, those are the situations where you integrate the unity function. All right, cool. Okay, good. Next. So units when you're integrating. So don't forget to consider units, because on exam problems I will always ask you for units. Yes.
But for the unity function, that's just before the dr, that stuff, right? Like the function we had one, or the other one.
This one?
This was the unity was one over here, right?
Yeah, the unity function, you're just integrating one, because I'm asking you to find volume. So you're going to integrate the function 1 over 3 dimensions. Similarly, I asked the same thing here. Derive the formula for the volume of a cylinder. I'm asking for volume, so again, you integrate the unity function 1. This was a different problem, so we didn't integrate the unity function. We integrated that specific function. All right. Next, units when integrating. So this will become more important when we do electrostatics. Now we are making sure that we want the units when you do integration. So as a general rule, after you integrate, the units are changed. And specifically, you will multiply by the units of the differential operator. For example, a lot of the times we are integrating over 3 dimensions, right? In 3-dimensional space. And so each one of the the coordinate systems, the unit for those coordinates is length, right? So let's say we're in a Cartesian coordinate system, and so we're using the MKS. Those of you remember, MKS system is meters, kilograms, seconds. So I'm giving you a particular example where suppose we know the charge density rho is given in units coulombs per meter cubed. The question is, what are the units for each of the following integrals? So let's go over one of this, each one. All right. So when we take the integral rho, the units for this is coulombs per meter cubed. Okay, that's charge density. When we take the integral of this rho function and we just do one integral, just the integral with respect to x, let's do the units here. This is going to be coulombs per meter cubed times meters, because this dx has a unit of meters. All right, so what does that come out to then? Coulombs per meter squared, correct. All right, similarly, when we do this, this is coulombs per meter cubed again. The units for this is meters. The units for this is meters. So what is the units for the integral? Coulombs per meter, got it. All right, and the same thing here. This is meters, this is meters, this is meters. This is coulombs per meter cubed. And so what is the units that we get out here? Coulombs, perfect. All right, so every time you do an integration, it's like multiplying. It's like multiplying by whatever the unit, the differential operator happens to be. And most of the time, what we're going to be doing in this class, it's going to be actually going to be representing distance. So they're going to have units of meters. All right. Do you have other questions about doing these integrals? Yes.
How can you tell what the unit is for the differential operator? Like, if how do you figure it out?
What are the units for the differential operator?
Yeah. How do you know? Like, how did you know? Say it wasn't given that it's meters. How did you know it's meters and not coulombs?
Okay. Yeah. So the question is, how would you know? How do you know the units for a differential operator? I mean, that's actually a good question. I'm going to tell you that for most of the problems that we do in this class, the x, y, and z dimension are actually going to represent space. Right? So you have to look back, to answer your question specifically, dx, dy, dz, what do they mean? How do you know what units they are? You have to go back and look at the original problem. What does dx, dy, dz represent? You have to ask yourselves first, what does x, y, and z represent? In this case, we go back to our x, y, and z axes. In all of these problems, in all of these examples that we've done, x, y, and z actually represents a location. So the units for x is going to be meters, the units for y is going to be meters, the units for z is going to be meters.
Gotcha.
So the units for the differential operators turn out to be the same.
Okay. Could you say that it would be the same as the units of the limits for the boundaries?
The units for the limits of the boundaries? Yeah, absolutely.
If they're the same thing or synonymous?
Yep. Because think about, like, when you're doing an integral, right, you have this dx thing. Dx, like, if you think about like derivatives and integrals, like dx represents a small incremental change in x, right? So you're going from x equals 4 meters to x equals 4.9 meters. I'm sorry, x equals 5 meters to x equals 4.9 meters, a small distance between them, right? So your dx is also, the units for dx is also going to be meters.
Okay, gotcha. Thank you.
Yep. Okay, so wow, I always cover, I always end up covering about like maybe 50%, 50 or 60% of what I plan to cover. So, but that's good, that's fine, because I think that making sure that you all know how to do these fundamental things is very important for the rest of the class. So we figured out how to do integrals, single integrals, double and triple integrals on scalar functions. I mean, we focused mostly on triple integrals, but doing single integrals, you already know. And double integrals are just, like one step beyond single integrals. So you do 2 steps instead of 3. We did the 3-step ones because they're the most complex. All right. So now what we're going to do is we're going to talk about line integrals and surface integrals. And these are relevant when we're working with vector fields. So the integrals that we did so far are referring to scalar fields, and now we're going to use line integrals and surface integrals to work with vector fields. So we're going to talk about why that's important, and then we're going to talk about how to calculate them. So the notation for doing line integrals and surface integrals is as shown. So line integrals they operate on 2D and 3D vector fields. Surface integrals operate on 2D and 3D vector fields. The notation is we will say that we're going to take the integral along a contour, and sometimes we just leave that c out. And we're going to take the integral of a dot dl. All right, and notice this is a vector quantity. So this is a vector field, actually, the vector field A. And we take the dot product with respect to what's called a differential length vector. All right. What happens when you take the dot product of two vectors? What do you get? A scalar, right? So the key thing is when you do line integrals and surface integrals too, both that same thing, is that you just have to do a step where you take a dot dl. Okay. When you take the dot product of the two, you're going to get a scalar. Now you have a scalar, you already know how to do scalar integration, right? So line integrals and surface integrals just involve one additional step where you have to figure out what A is, you have to figure out what DL is, you do take the dot product between the two, and now you're just left with a scalar function. And you already know how to do the integrals of scalar functions. All right, it's just one additional step. Surface integral, same thing. This is also a vector field A. Right, so I will just put the arrow here like this. Now this one is called a differential surface vector. All right. And again, you're going to take the dot product between the vector field A and a differential surface vector. Dot product will give you a scalar quantity, and now you are just taking the surface integral of a scalar field. So surface integrals are going to be two-dimensional integrals. And if we want to be totally explicit about it, we would just put the second integral sign to denote that it's a double integral that we're going to be taking. Even if you don't have that, it's implied because wherever you see this ds, that means a differential surface, and a surface, of course, means you're going to be integrating over 2 dimensions. L refers to a differential line, so that refers to a single dimension. All right. Okay, so we're gonna see if we can do this in the next 5 minutes. Calculating the tangential and normal components of a vector on a surface. This is important because when we do these problems in vector fields, figuring out this dl and the ds, it requires us to be able to work with tangential and normal components of vectors. So here's the thing. We have a 3-dimensional problem. The tangential and normal components can all be used using these things called projections and dot products, which we talked about before. Projections and components, actually. We talked about that at the beginning of the module, so I'll just go over that real quickly. If you want to find the projection of something, you have to first find the component and then multiply it by the normal vector. Okay. Okay, so we have this surface. This is a 3D surface, or it's a 2D surface rather. Sorry, it's a 2D surface in a 3D space. All right, so think about this as being, like a rug or something. So we have this vector E. Okay, this is the vector E. And that vector, assume that that vector is pointed in some arbitrary direction. It's not necessarily orthogonal or parallel to the surface. It's just some random vector E that's pointed in some random direction. So what this slide is showing us is how to calculate the tangential and normal components of E. So if you want to calculate the tangential and normal components, here's what they're defined as. The normal component, the way that you think about this is that every surface, this 2-dimensional surface has a normal vector n. And that's what this is. This is the normal vector, and that's denoted by this green arrow. So you can find the component of E that is normal to the surface, and you can find the component of E that is tangential to the surface. So the normal component is shown here as E sub n, and the tangential component is shown E sub t. The normal component is a component of the vector that is perpendicular to the surface, orthogonal to the surface. And then the tangential component is the component that's tangential or parallel to the surface. All right. And the total the total vector can be expressed as the sum of the two. There's a tangential and normal component. All right. So how do you figure out the tangential and normal components? Well, we already know how to figure out the normal component because of the dot product. Okay. In order to find the normal component, we're going to take the projection of E on n hat. All right, E is pointing in some random direction. We want to find how much of E is on this n hat. So we break down E into two components. We break it down into a normal component and a tangential component. We want to find out what the normal component is. And it turns out we can do that using this projection. So the normal component is equal to the projection of E on the n hat vector. That's equal to the component of E on n multiplied by the n hat vector. This is stuff that we talked about before when we talked about projections and components. And the definition of the component is E dotted with n hat. And this works because n hat it has a length of 1. So the component just becomes the simple definition here. Remember that the component, E dot n is equal to the magnitude of E times the magnitude of n hat. E dot n hat is magnitude of E, magnitude of n hat times the cosine of the angle between them. But this n hat is equal to 1. So this n hat goes away, and you're just left with the magnitude of E cosine of theta, and that's the angle between them. All right, so that's this formula up here. E dot n hat is just the magnitude of E times the cosine of the angle between them. So this is a mathematical definition for figuring out what the normal component is. And then if you want to find the tangential component, you just use this formula up here. E is equal to the tangential plus the normal component. So the tangential component is just the total E minus the normal component. And you're left with this formula here. So unfortunately, it looks like we're out of time. I have an example here that I'd like to do, but we're going to have to do that on Monday. So I think we'll have to end class here. We'll have to do this on Monday. Now, I want to make you all aware that there's a new homework that is posted already. If not, it's going to be posted this afternoon. That will be due next week, next Wednesday, and you will definitely need that to prepare for your exam. And I'm going to give you some additional problems too to prep for your exam. So make sure you do that and are comfortable with that. And that'll be like your last set of practice problems before the test. All right, thanks for your attention. Any questions, let me know.
Only thing was, there was a question in here that you wanted us to use Python. Did you want us to email it to you? Like, I didn't know if you wanted like the actual graph.
Yes, I did want that.
You want me to? I didn't think I saw something that's submitted online. So we just email it.
If you could print it out and add it to your homework, or just email it to me and I'll forward it to the grader.
Okay.
You are currently the only person in this conference.